Hello friends, I am Professor M.P. Zhanze, Department of Mathematics, SNJB's KK Chart, SMGL Commerce and SPHJ Science College, Chandwad District, Nasik. Today we have to see one of the important topic of linear algebra, that is vector space. Now what is vector space? A vector space over R is a non-empty set with operation addition and scalar multiplication, satisfying closure under addition and scalar multiplication, commutativity, associativity, additivity, additive inverse, distributive two forms, associativity of scalar multiplication, that 1 into UR is equal to U bar. This means that a vector space which satisfies the 10 axioms, 2 addition axioms, 2 closure axioms, 4 addition axioms and 4 multiplication axioms with distributive properties. Key idea: linear combination in phi, scalars are real numbers unless stated otherwise. Vector space axioms, just we have seen that C1 closure axioms, that U V W belongs to the V and K L are the scalars, then U plus V belongs to V, and any scalar into a vector also belongs to V, that is closure axioms. Addition axioms, it is commutative, U bar plus V bar is equal to V bar plus U bar. Addition is associative, U bar plus V bar plus W bar is equal to U bar plus V bar plus W bar. And 0 is additive element, 0 plus U bar is equal to U bar. There exists a negative element, U bar plus minus U bar is equal to 0 bar. And 4 multiplicative axioms, that scalar K is a scalar which distribute over addition, K into U bar plus V bar is equal to K U bar plus K V bar, K plus L U bar is equal to K U bar plus L U bar, and it is multiplicative also. So multiplication properties also satisfied there. Multiplication with respect to associative with respect to multiplications, KL into U bar is equal to KL U bar, and one is the multiplicative identity, 1 into U bar is equal to U bar. Some examples of vector space: Rn, order n tuple with commutative addition and multiplication, M n cross n matrix with real entries, Pn the nth degree polynomial, and that function space, real valued function space, f plus g of x is equal to f of x plus g of x. All these are the standard examples of vector space. Unusual examples: positive real numbers, x bar plus y bar is equal to x into y, and kx is equal to x raised to k. If we define the addition and scalar multiplication is also vector space, we can verify all these 10 axioms. For examples and non-examples: infinite sequence, symmetric matrix, n cross n symmetric matrices, direct sum are the examples. Non-examples are there: set of natural numbers, no 0 and no inverse, therefore it is not a vector space. Z not closed under real scalar multiplications, and the order for x y such that x equal to 1, non-zero vector, that is also not a vector space. Second degree polynomial, no 0 polynomial is there, so therefore that is not a vector space, it is not closed under addition. Now the 0 vector is unique, the negative of each vector is also unique. 0 into V bar is equal to 0 bar, minus 1 into V bar is equal to minus V bar, and if K V bar is equal to 0 bar, then K equal to 0 or V equal to 0. These are the easy proof, basic properties of vector space. Now subspace, a non-empty subset W is a subspace if itself is a vector space under the same operation. It is itself is a vector space under addition and scalar multiplication. It should be closed under, in easy language we can say it is closed under addition and scalar multiplication, that is called subspace. W is subspace if and only W is non-empty, closure under addition, closure under scalar multiplication. 0 vector must be there, it should be non-empty. W is non-empty, equivalently 0 belongs to W. This is subspace test. Why the other axioms commutative associative are inherited from the V? This is the very important result from subspace, that we have to prove only closure under addition and scalar multiplication, and all the remaining properties remaining axioms of vector space are inherited. In R square, say x plus y equal to 0, line through origin, example of subspace, x axis 0 subspace. In function space f of a equal to 0 and p nth degree polynomial p is also a subspace. Union versus intersection. Intersection of two subspaces is always subspace. Union of two subspaces is not necessarily a subspace. Linear combination and spanning. A linear combination of vectors v1, v2, vn is alpha 1 v1 bar, alpha 2 v2 bar plus 2 up to alpha n vn bar, and the set of linear combination is called span of or linear combination of vi. If two vectors are there, then we can say one is scalar multiple of other. But if there are n vectors, we use the terminology that linear combination, and any one can be expressed in the linear combination of rest of the vector. This is important result in the vector space. In R square, that 1 0 0 1 standard basis for R square, it spans R square, standard basis. Now linearly independent vector, if v1 v2 vn are linearly independent, then there exists scalars c1 c2 up to cn all 0, otherwise they are linearly independent. This is the definition of linearly independent. In a matrix determinant notation also, if determinant is equal to 0, then set are linearly dependent, otherwise it is linearly independent. Determinant not equal to 0. In R square, two vectors are independent if they are not collinear. In R cube, three vectors are independent if they are not coplanar. Basis of vector space, it should be linearly independent and spans V. Once again, same definition is there. Standard basis for R square. For matrix 2 by 2 entries with real entries, there are 4 bases. Therefore, dimension of M 2 by 2 matrix with real entries is 4. Nth degree polynomial has one more basis, that 1, and therefore the dimension of nth degree polynomial is n plus 1. And dimension of Rn is n. Find the coordinate vector if the vectors are given with relative basis. The solutions, first of all, we can express in the linear combinations and solve the system, and we get the relative vectors, the coordinate vector, relative coordinate vector. Easy solution is there. Now a non-zero vector space is finite dimensional if it has a finite basis. The dimension of phi, number of vectors in any basis. Number of vectors in a basis, number of basis vector is called dimension. Dimension of 0 is 0, dimension of Rn is n, dimension of nth degree polynomial is n plus 1, and dimension of n by n matrix is mn. Actually, invariance, any two bases of finite dimensions have the same number of vectors. Important result. Dimension of phi equal to n. Any set of n linearly independent vectors is a basis. Any set of n vectors that spans phi is a basis. A linearly independent set with less than n vectors can be extended to a basis. And if W is a subspace of phi, then dimension of W is less equal to dimension of phi. That if and only if W equal to phi. Key facts of the dimensions. Here, two vectors in R cube is independent but not a basis, because basis it should be, example is there, 1 0 0 to get a basis. Now row space, column space, null space are there. Just reduce matrix into echelon form, then we can find the row space, column space and their corresponding basis. Rank, number of non-zero rows in a matrix. Once you reduce the matrix into echelon form, then dimension of row space is called rank, dimension of column space, and dimension of null space is nullity. So find basis for null space, just consider augmented matrix reduced into echelon form, then we can find the null space, and that is nothing but the nullity of a matrix. Rank nullity theorem, for M by n matrix A, rank plus nullity equal to n, the number of columns. Rank nullity theorem, earlier matrix A has a rank 2 and nullity n equal to 4, nullity equal to 2, n is the number of columns. So using the above theorem, we can calculate the nullity. If n greater than m, this means that null space contains a non-zero vector. Rank A always less equal minimum of mn. Vectors u v are said to be orthogonal if their dot product is equal to 0. Two subspaces v and v are orthogonal, dot product equal to 0 for every u belongs to u bar and v belongs to v. fundamental orthogonality. In Rn, the row space of A, the null space of A are orthogonal complement, and every vector in the row space is orthogonal to every vector in the null space. Similarly, the column space of is orthogonal to the left null space. So orthogonal vectors, and orthonormal also, then their norm equal to mod equal to 1, then we say that corresponding vectors are orthonormal. The four fundamental subspace are there: row space Rn, null space Rn, column space Rm, and left null space. So if M-bind matrix A has rank R, then dimension is given in the table. Row space perpendicular to null space, column space for left null space, and rank nullity theorem we can use. Some exercise are there from your text. Thank you very much.